In this section, I want to talk about the ideas of logical formulas that are either always true or always false. I'll give some examples in a second, but just to tell you, we call logical formulas that are always true, we call them a tautology, and ones that are always false, we call a contradiction. So let me give you an example of a tautology, something that's always true. I'll write it out as a logical formula, just in terms of, say, P, but I'll explain it in words, giving some meaning to P in a second. So something like P or not P. That's an example of something that is always true. You can imagine if I told you if P was I had coffee for breakfast, this would say I had coffee for breakfast or I didn't have coffee for breakfast. There's no way I can be lying to you with this. This is just always true. And remember, with an or statement, the or statement is true when at least one of the two constituents are true. And because these guys are the negations of each other, one of them is, of course, going to be true. So this is an example of something that is a tautology. It's always true. A contradiction is something that is always false. So pause the video now and try and think of a nice simple example of a contradiction this time. Maybe use this example of a tautology as something you can build off of or modify. And you might have a different one than what I come up with, but try it yourself. See if you can come up with a statement that is always false. Okay, now that you're back, the one that is probably the simplest that is always false, a contradiction, is something like P and not P. Remember that an and statement is false if one of the two constituents of the and is false. It's only true if both are true. And because we have a statement and its negation, only one of these can be true. There's no way that both of these can be true. So this is an example of a contradiction. Let's do something a little more complicated now. Let's use a truth table to show that this compound statement, P and Q implies P or Q, is a tautology. So again, we're going to work with the truth table just like we did in previous examples. We're just going to write down all possible truth values for P and Q, and we are going to use our order of operations to kind of do this in the correct order, and we're good to go. So we need P and Q. Let's write down those truth values now. So that's all possible combinations of when P is true or false and when Q is true or false. Okay? And what do we need? We need P and Q. We need P or Q. And then we need the implication of those. So let's figure that out. So we need P and Q. We need P or Q. And we need the implication of that. P and Q implies P or Q. Okay. So let's go ahead and fill this in. So we know that the and statement is only true if both of its constituent parts are true. So that's easy. That just comes straight from the definition. And P or Q is false exactly when both of its constituent parts are false. So that's false, and the rest is true. Okay. So here we have P or Q implies, P and Q implies P or Q. Remember an implication, an if-then statement. If P and Q, then P or Q is false exactly when the if part is true, and the then part is false. So let's look in this situation. We have true, true, which is true. Here we have false, false. So that means that the if part is false, so there's no way for this to be true. So it's going to be true again. In fact, I'll just talk through the rest of them. Here we have false, true. The if part is false, so there's no way that an implication can be false if the if part is false. And same with this one. So for all of these, we have true. And since we have that no matter what truth values are here for P and Q, we have that the truth of this statement here is guaranteed. It's just true always. This is a tautology. Let's do one more example, and let's do a contradiction. So same idea, but instead of showing it's always true, we're going to show it's always false. So now we're going to do a different example in the next video. Note that down here there's a small typo in here, so don't worry about this example here just yet. We'll do something that doesn't have a typo in it. This, in fact, is not a contradiction. So if you want to do this example, show this is not, or this arrow should go here. This is not a contradiction if you want to do it as an exercise.